If you haven't had a chance to watch part 1, I highly recommend doing so, even if you already have some understanding of logistic regression. Because now, it's time to get serious. Going from 2 to 3 classes is conceptually very challenging. The rare lectures that attempt to explain multinomial logistic regression are very math-heavy, relying on it to do a lot of the work. But math, despite its intended purpose, can often distract from the big picture. We're going to do things differently. This is how I think about logistic regression. Part 2. So far, we only know how to distinguish one thing from another thing. So with more than 2 classes, it's only natural that we should try running logistic regression multiple times to distinguish each class from the rest. Let's say, for example, we have 3 classes, green, blue, and purple. We can use logistic regression to distinguish green from the rest, blue from the rest, and purple from the rest. We fit the following sigmoid function to green, to purple, and to blue. Notice that the sigmoid function isn't very pronounced for blue. This is because a more pronounced sigmoid function would result in granting high probabilities of being blue to points on the left or right, which clearly aren't blue, which would mean making more significant mistakes, which would deflate the overall likelihood of seeing the data we saw. So logistic regression finds a less pronounced sigmoid function here. Once we have our 3 models, we predict the class whose model has the highest probability. And this is fine and works pretty well. It's at least deserving of the name 1v-rest classification. But wait a second. These are no longer probabilities because there's nothing guaranteeing they sum to 1. It's also strange that in the blue region, we're very sure that it's not purple and very sure it's not green, but we're not very sure it's blue. What we're looking for is a way to distinguish each class from each of the others instead of generally from the others. A subtle difference that's easier to see in 3 dimensions. Distinguishing blue from the rest using logistic regression means fitting a sigmoid function that looks like this, and a decision boundary that is a line. What we would like to do is to simultaneously distinguish blue from purple and blue from green, somehow combining both a sigmoid function for blue versus purple and another sigmoid function for blue versus green, creating a decision boundary that looks like a V. Can we adapt the sigmoid function so it can incorporate not 1, but 2 thresholds? By adding an extra exponential to the denominator, we get a sort of sigmoid function that varies in 2 different ways. This seems like exactly what we're looking for. Depending on how you look at it, it seems like there's a sigmoid function to distinguish blue from purple and one to distinguish blue from green. By adjusting the parameters of each of the distinct linear functions, we can adjust the V-shaped decision boundary. But how do we use this function for classification? A high probability for this function means a high probability of blue, but we don't know if a low probability means a high probability of purple or high probability of green. Since we can think of this function as a combination of sigmoids, we just need to figure out how to draw out each specific sigmoid component. To understand how, recall how the sigmoid function worked for 2 classes. Let's say we model blue using logistic regression. Yes, the probability of purple is 1 minus the probability of blue, but doing some math, we see that they have a much nicer relationship. Blue is proportional to purple. To get the probability of purple from the probability of blue, we just multiply by the exponential that characterizes that sigmoid function. We can see this geometrically too. The probability of blue is symmetric to the probability of purple around the boundary. With 3 classes, we can extract the probability of purple by multiplying by the first exponential, and the probability of green by multiplying by the second exponential. Meaning that for a given probability of blue, the probability of purple should be symmetric around a purple boundary, and the probability of green should be symmetric around a green boundary. We now know how to adapt the sigmoid function to distinguish one class from 2 others. We also know how to get the respective probabilities of each of the other classes by multiplying by the correct exponential. But there's one major problem. How did we know that blue was the class to model using this adapted sigmoid function? Turns out that it doesn't matter what class we choose. Intuitively, this is because the adapted sigmoid can take on many different shapes depending on the parameters that define it. Mathematically, notice what happens if we divide the numerator and denominator of each of these fractions by the exponential that characterizes the probability of purple, for example. The adapted sigmoid appears to now model the probability of purple. So the versatile shape of the adapted sigmoid combined with the proportional relationship with the other classes means that any class could have been chosen, not necessarily blue. To better understand how the parameters affect its shape, let's go back to our one-dimensional example. The adapted sigmoid function that can distinguish blue from purple and green is the following. Notice the sign of the exponents. One is negative and one is positive, combining two opposite-facing sigmoids so they meet in the middle. If the signs were both positive, we would be combining two sigmoids in the same direction, thus creating an amplified sigmoid function. If we run logistic regression and look at the probability of purple obtained, why does it look like a sigmoid and not like the adapted sigmoid that characterizes blue? Dividing the numerator and denominator by the exponential that characterizes the probability of purple, we see the formula for the adapted sigmoid function appear. But both exponentials in the denominator have the same sign, and so we get an amplified sigmoid function. We only get an adapted sigmoid that looks like blue when we have exponentials of opposite signs in the denominator, which, given we have three classes, can happen at most once. Some libraries, like stats models in Python, will choose a class at random to be modeled using the adapted sigmoid. It's then up to gradient descent to find the parameters that shape the adapted sigmoid in the correct way for each class. Other libraries like sklearn use a different but equivalent formulation where no class is special. The probability of each class is defined by the exponential of a specific and unique linear function. Dividing by the sum of these exponentials ensures that all these probabilities sum to 1. This function as a whole is called the Softmax Function. Notice that it's equivalent to the previous formulation that uses a default class, since we can simply pick a class and divide the numerator and denominator of every probability by the exponential that characterizes it. I know what you're thinking. Why exponentials? Couldn't we achieve this with any function so long as we normalize things so they add up to 1? Great question. And yes, you're absolutely correct. There are some nice properties about exponentials that make it a compelling option, but it's not the only viable option. To recap, we now have a single process to predict 3 probabilities using this softmax function. With 4 classes, we'll need another of these exponentials. With 5, yet another, etc. We update the parameters of each of the linear functions similarly to when we had 2 classes. The probability of seeing the data we saw is the probability of the first data point times the probability of the second, etc. Where each of these probabilities comes from this softmax function. In part 3, we'll learn how to make sense and interpret the parameters of logistic regression, both from a statistical lens and a machine learning lens. I hope this helped you better understand how logistic regression works with more than 2 classes. Leave a like, subscribe, and help me share this knowledge around if you found it helpful.